Okay, trig substitution. We are using trig functions to make a sub. It's a kind of like a U sub, but it's slightly different. Okay, before I start, there are so many different techniques of integration now. So much different levels of integrity. Wait, what's the meaning of the word integrity? Once again, ability to integrate, of course, right? So we have got a lot of integrity that we never had before. I mean, there's like direct integration. If you know the antiderivative, you can find it. And there's a U sub, right? And then we did integration by parts. And then we did other like trig expression integration, many different techniques. And today's stuff is called the trig sub as opposed to U sub. And there's a thing called partial fraction that's coming up later. I mean, it's like there are so many different ones. And the most common question is, how do you know which one to deploy when? You should kind of feel it, but, when in doubt, if you just can directly do it, that's number one. Number two is U sub. U sub is nice. It's quick enough, okay? But whatever you do, trig sub is always the last, okay? This is the worst one. They are generally very, very nasty. So don't do it unless you have to. Okay, that's what I have to say about trig sub. This is absolutely the last resort. Okay, just so you know. Okay, then with that, I will show you how to do trig sub. Okay, so suppose this is ugly and we are stuck right here, right? Like, how do we, right? And then, of course, nobody's going to claim this is ln of square root of 1 minus x squared. God, no, you're not gonna. That's negative 10 right there, right? No, never. 1 over x is the only thing that becomes ln, so it's like, forget it, okay? So let's here. See, if you have this kind of thingy, let me rewrite it a little bit. So it's basically this, isn't it? Now, what is my, why is my handwriting so ugly? Let me start over. I don't know why I'm so anal, but I am. I'm gonna write it on top again. 1 minus x squared, okay? See, these two terms and the square root to top it off in the denominator is very, very ugly. We get stuck, right? So here is, when everything else fails, we try this. X is sine theta. And this was like briefly in your pre-calc book. Do you remember forgetting it? Now, what is my motivation of doing such a thing? It's this ugly term in the denominator, what that does. Okay, let's see how this thing evolves then. 1 minus x squared. Once you substitute sine, this becomes 1 minus sine squared. Eh? Now somebody tell me what 1 minus sine squared is?
Cosine squared?
Cosine squared, of course, right? That's the motivation. These two terms have been switched to one term, which is better than 2, especially in the denominator. And then, what is this thingy? What's the square root of cosine squared theta? Is it this, or is it absolute value? You. What do you say? Because this happens, see, not only that, and this is easy to forget, but we need that dx, right? Dx is a derivative of this thingy, right? So dx over d theta, if you will, that is cosine theta, d theta as well. So what happens if you substitute it? Okay, the denominator becomes this, and the numerator becomes this. They almost cancel, right? So what is that thing? What is that thing, right? Let's just recall what that, whenever you have something that looks like that, this is the case. See, cosine theta over cosine, anything x over absolute value of x. Basically, this is 1 or negative 1, depending what these things are, right? If cosine theta is positive, then this is 1. If cosine theta is negative, then it becomes -1 now, doesn't it? Ew. Is cosine positive or negative, or do we have to have a case 1, case 2 split piecewise integral? Oh my God, right? Let's go back up. When we say tricks up like this, what that means, what we are really doing is this is like a u sub, really. Instead of u, theta is equal to inverse sine of x is what we're really doing. We are omitting that part. Now let's talk about domain and range of that thing. What is somebody tell me the domain and range of inverse sine? Huh?
It's negative pi over 2.
Negative pi over 2 here to pi over 2 is the range. Well, what about the domain? Okay, answer my own question, right? Okay, that's it. We are not considering outside of this range, and that's it. Okay, that's implied here. Now, so this is first quadrant or fourth quadrant now, isn't it? It could be negative, you have to worry about it, but cosine theta in first quadrant is positive, this case. What about the cosine theta in fourth quadrant?
Positive.
That's positive again. This doesn't exist now, does it? Wow, that's so nice. Meaning they just cancel. So this whole thing just is 1. This is the nicest integral there is, well, next to 0. So this just becomes theta. Let's see. Well, what was theta again? Inverse sine of, you know what I'm saying? Now, some of those questions in the previous sections that, oh, do we have to memorize this? Because if you remember, if you take a derivative of this inverse sine, you get exactly that thing back. Do you have to memorize? No, you don't. Now you don't, right? You see, here's that someday that I promised you that we'll go over this whole thing, trig substitution, okay? Now, the next question I get a lot is, could we have used cosine instead of sine? And the answer is yes, it works out exactly the same way. It gives you exactly the same answer. The reason that most sane people never use cosine, and I've never seen it, is what's the derivative of cosine? Negative sign. You pick up a negative sign. But doing this calculation, it cancels and it turns out to be positive. But there is that little possibility of screwing up a sign. So choose the safe one. I'm a negative guy. I love negative numbers and all. But when I do this, I always use sine, so I just keep positive numbers only. You know what I'm saying? Any question on trig sub and what to use when? So whenever you see this form, this thingy, then you use sine so that it combines. It depends on Pythagorean identity of trig. You get it? Okay, let's move on then. So we have this now. Isn't that nice? For some reason, this thing is so sensitive to palm movement. So if we have dx, and then it doesn't even want to write dx over now 1 plus x squared. Okay, I mean, even if we didn't have a hint, we'll let x to be tangent theta in this case, which is really theta u sub. It's kind of like a u sub. Theta is equal to inverse tangent of x is what we're doing with all that restriction. Then our motivation is really this one. What does that one? Because those two terms better combine to 1. How do you like it? What is that thingy? That thing is secant squared theta, isn't it? And this one, we are not even square rooting, is definitely positive, is secant squared. You get it? And then, before you do anything else, we need the derivative. We need dx. You get it? Don't forget, that's easy to forget. So dx, what's the derivative of tangent? Or secant squared theta again? Wait, we are taking this thingy over that thingy? Yeah, we are. So, do you see this thing cancels and just gives you this nice integral again? Oh my God, this is just too good to be true now, isn't it? No, generally trig subs are not this nice. You will see in the last example. These are the nicest cases, okay? And this, you had this question in homework before, but I told you not to memorize, don't worry about it. So this is theta plus c, and what was theta? Inverse tangent of x. Bang. How about that? Good? Y'all good? Any questions before I move on to something? These two are very nice. Next one is not as nice. Okay? Let's look at this one. This one is kind of hideous. Okay, let's do this. So we have, I don't know why this computer screen does that. See? As soon as I touch it, it's like so sensitive to palm. Integral of dx, and then we have x here, and then square root of x squared minus 1. Okay, that's x squared minus 1 is the key. So even if it doesn't tell you the hint, we should know x is equal to secant theta. Okay, with this domain and restriction of inverse secant of theta. And then let's see what this thing does. X squared minus 1, of course, will be square root of secant squared theta minus 1. What is that thingy? Of course, that's tangent square, isn't it? Say yes. Okay, and tangent squared theta, this one is not tangent theta. We have to. What? Why? Okay, this one I'm going to bring it down a little bit so I can write down that inverse tangent. The reason for this one is really what we are doing is theta is equal to inverse secant of x. And can x be negative? Yes, absolutely it can. You know what I'm saying? X could be negative. That means theta, what is the range of this thing? First quadrant and second quadrant. See, in first quadrant, tangent is positive. In second quadrant, this is negative. You see, now we have to worry about this. Problems say x is positive just to be nice here, but we cannot really assume that. Okay, then let's just plug it in and see how this thing simplifies. So numeral, oh, we need dx, so let's calculate dx. dx is derivative of secant, so this is secant theta tangent theta a. So let's write it, secant theta tangent theta d theta over x. X is secant theta, so we have secant theta, absolute value of tangent theta. See, secant theta can cancel, but we have this thingy. And that's a lot of headache. Dang it, right? Okay, let's think about what that thingy is. So I'm going to write it here. Tangent theta over absolute value of tangent theta. Right? That is, of course, 1 if tangent theta is positive and negative 1 if tangent theta is negative. Okay? I'm going to draw this triangle. And then we know better not to put the variable up here, right? 1 over x. Remember this? This is 1, and this angle is theta. And x could be negative, so it could end up here, right? Remember this headache when we are differentiating inverse secant function? Yeah, we have this situation. Okay, so if theta is in second quadrant, let's say 3 pi over 4 or something, this is negative. So you tell me, you see x is negative, and then this whole thing is a second quadrant, isn't it? Other way of saying tangent theta is negative is saying x is negative, isn't it? So we can say x is positive and x is negative. You know what I'm saying? But in order to be a little more professional about it, what's the domain of this thing? It starts from 1 to infinity that way, or -1 to negative infinity. It cannot even be less than 1. You see, if you put something less than 1 inside, you have an imaginary function, right? So instead of this, in order to be more professional about it, it doesn't want to select. Really? Why wouldn't it select? Okay, just use the eraser option. So this is, if you write just 0, that's fine. But I want to be a little more technical. Okay? Okay, so this thingy is like 2 different cases. Holy cow. Okay, why don't we do those 2 cases separately? Okay? So first, red color, case 1. Case 1 here. It's frozen. Case 1. X is more than 1. Okay? Then what we have is just 1, right? And that becomes theta plus c. And what's theta? Inverse secant. You get it? Very good. Inverse secant over there. Case 2. X is less than -1. And then this thingy doesn't become that, we have a negative sign. You get it? Because of this piece now. Good. Okay, then this becomes negative theta plus c. And that is just negative c. So this is a piecewise answer in the integral. You get it? How about that? Very good.
Mr. K.
Yes.
I just have a question about how you put both constant as plus c. Is that fine, or one has to be the other?
No, it's fine.
Other.
I mean, it's
okay.
It's fine.
Okay, so you wouldn't really want it.
D, but yeah, no, it's okay.
Okay, so for constant, we can just put plus c all the time. We don't have to separate them, right?
Yeah, unless you did something to that constant, like divide by 2, then you can call it D. You know what I'm saying?
Yeah.
Yeah, but people are generally not that picky about constants. Any other questions before I take application? Well then, finally, we can derive the area of the circle formula. What is the area of the circle from geometry?
Pi r squared.
Pi r squared, right? Did anybody sit you down and explain it to you why is pi r squared? Today is the day. This is why area of the circle is pi r squared. Okay. First, we need, is that exactly in the center? Yeah. Okay, we need the equation of the circle, right? Let's say this area is R, -R. So then this thing is x squared plus y squared is equal to r squared, isn't it? And then we take one rectangle, let's say right here. And then we find the area of that thing. This is what I call dA. And this side is y, and this side is dx, isn't it? So that's y times dx. You see, if you just integrate the function, it gives you area underneath it. We can do it from here to here. Then if I say this y is equal to, not plus or minus, just the upper side. You know what I'm saying? If I do that, it's just that one, then it gives us this entire area, then we can double it. You get the plan here? Okay, so we plug it in here. So we get square root of r squared minus x squared dx. You with me so far? Okay, then shall we figure out the area? Now, instead of doubling it and going from negative r to positive r, we have a very even function, right? And 0 is our favorite number, so why not do it this way? And then quadruple it. You get that? This will only give us area of this first quadrant, and then we can quadruple it to make it entire circle. Still good? Okay, and then this, of course, is r squared minus x squared dx here. Ah, there's our trig sub. You know what I'm saying? So, what should x be? Now, initial thought is this. Oh, that should be, of course, sine theta now, right? Not quite. You'll see why that's not quite, but like how, because I get this question. How do you know when to put? You just try it, then you know. Watch this. So this is r squared minus space sine squared theta if you plug it in, right? And then you get stuck right here. Ah, that doesn't quite do Pythagorean identity. Don't you wish we have an r squared here? That's so much better now, isn't it? Then you can common factor, so you get 1 minus cosine squared. So that's why we insert r here. You get it? Why do you insert it? Because we need it. I mean, the whole thing is to make this thing one term, so it's convenient. Since we are doing a trade-off, two terms are nasty, so we want to trade it with a one term. And in trade-off, we convert this to trig function. Trig functions are generally not as nice. You know what I'm saying? So that's what trig substitution is all about. So this thingy, oh, I still have to say what that is, right? Let me move it. Okay, let's do it this way. So this square root of r squared minus x squared happens to be this. And now r can be common factored. So we have r squared, then 1 minus sine squared theta. You know what I'm saying? And then that is r cosine theta. And like we did before, we don't have to worry about the absolute value here. Because cosine, this is either first quadrant or fourth quadrant, and cosine is positive. Good? So that's a nice expression. And let's not forget dx. Dx is, of course, the derivative of this thingy. So that is r cosine theta d theta. Now we plug it in. So we have this thingy, which is r cosine theta, and dx, which is r cosine theta again. So we have r squared cosine squared theta. So far so good. Now, one more thing. It's exactly like u sub. When we change the variable from x to something u, we have to change this limits of integration because x varies from 0 to r. Theta doesn't vary from 0 to r. You know what I'm saying? You kind of see where. So we have to change these things as well. So you substitute 0 here. That means sine theta has to be 0. So theta is 0. So this is 0. Good. You substitute r here. It's a trig equation. So cancel r. So which means sine theta is equal to 1. You get it? When is sine theta equal to 1? How about that? Okay. Now we go. Wait a minute, this thingy, do you remember how to do this from yesterday's lecture? The same thing that will be on 5 different tests. What is cosine squared theta? Let's get it down here. Cosine squared theta, after order identity, was what? Somebody say it.
1 minus cosine 2 theta.
Almost 1 plus cosine 2 theta. Okay? So we plug it in here, right? And then this 2 is going to cancel with this thingy. So we'll have 2. And then we'll write r squared. So far so good. And from 0 to pi over 2. And then this will be 1 plus cosine 2 theta. You with me? Now we integrate. We can show our integrity now. So we have 2r squared. And this thingy becomes theta plus, and this thingy becomes sine 2 theta. Reverse chain rule, 1/2. And from 0 to pi over 2. Still with me? Say yes. Okay, now we evaluate. So 2r squared, you plug in pi over 2. What happens if you plug in pi over 2 here? What is sine of 2 over 2? That's a sine pi, which is 0. Minus, if you plug in 0, that's 0. If you plug in 0, that's 0. And that, of course, is pi r squared, as I promised. Wow, what just happened? Now we know how to derive every other circle formula. All it took was a little bit of integrity. Don't you feel empowered now? Now you get this sense of like, my force is getting stronger. Force will be with you. Wait, that's the wrong side. The dark side will be with you always. So this thing tells me what my motivation for x is. So I'm gonna choose x value to be 2 and sine theta, right? And I usually do d theta first, or dx first, to get away, and you'll see why. This becomes 2 cosine theta, d theta, and then this thingy, the complicated one, my motivation. Why did I put square root? 4 minus x squared and to the 3 over 2 power, right? This thingy becomes 4 minus 4 sine squared, right? 3 over 2, which becomes 4 cosine squared. You know what I'm saying? So far, so good. And that thing, of course, is 8 cosine cubed theta. Too much trick identity? Nima, question?
I can't see your stream. Could I leave and then join back?
Yeah, do that. I'll let you back in. Okay, everybody else with me? Okay then, let's substitute and see what happens. So what we have is dx, so this thingy over this thingy. That's why I write dx on top. So this over this. You know what I'm saying? 3 over 2 power factored in. You with me? So we have 2 over 8. So we have 1/4. Oops. So we have 1/4. And then we have secant squared. Do you see that? This over this, so we have 1 over cosine square. And by the way, I've seen this in previous years. Somebody did this. 1 integral 1 over 1/4 cosine square theta d theta, and of course that's ln of cosine squared. Don't do it. This is negative 10 points. Okay. No, 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 never, never, never. Okay. So this. Now, what is the antiderivative of secant square? That's tangent, isn't it? So this is 1/4 of tangent theta plus c. You with me now? Okay, now what we have to do is this problem from last year. This is 1/4 of tangent of your theta, and theta happens to be inverse sine of x over 2, isn't it? So it becomes this problem. You know what I'm saying? We don't have to write this line, but that's kind of what it is, right? Theta is this is a theta and x relationship. So in order to figure that out, we have to draw this triangle now. So let's do it here. Triangle can be in the first quadrant or in the fourth quadrant, correct? And then this is theta right here, and this is x, and this is 2, right? That way, up here, x over 2 is equal to sine theta. You get it? And then this side right here, that thingy right there, is square root of 4 minus x squared. Eh? Say yes. So what we have here is tangent of that angle, and tangent is, of course, this thingy over that thingy. So we have x over and square root of 4 minus x squared plus c. All good? You all with me? Okay, now then we move on to number 15. Okay, number 15. This thing tells me, oh, you, right? First thing we have to do is we have to complete the square. So let's complete the square. So this is equal to integral of dx over square root of x minus 1 squared, and then we have minus 1a. Too much algebra? You want me to show you how to do that while I'm at it, or do we all know how to complete the square? Okay, nobody put the hand up, so let's just assume you know how to do that much. And then this is my motivation now, right? That thingy. So I'm gonna let x minus 1 to be secant theta now, okay? So dx, still take a derivative, and derivative of secant is secant tangent d theta, and this is my main motivation. This thingy, x minus 1 squared minus 1 will become square root of, this whole thing is secant theta, so secant squared minus 1. You get it? And that, of course, is not just tangent, but absolute value of tangent, eh? So that will create the headache for us now, right? It's the absolute value. Why, how come you didn't have absolute value here? Because the sine exists in first quadrant and fourth quadrant, where inverse sine, that is, because we are really making a substitution with the inverse sine. Theta is equal to inverse sine x over 2. And then we have a cosine here. Cosine is positive in both of these quadrants, so we got lucky. But here, inverse secant exists in first and second quadrant, and tangent is positive in first quadrant and negative in second quadrant, so we do have to worry about this thing. You know what I'm saying? Okay. Well then, you, right? Okay, so let's substitute and see what happens. So we have dx. Dx is this thingy, right? So we have secant theta, tangent theta, over absolute value of tangent theta, d theta. And that's a major headache now, isn't it? So now we have to split this into two cases, when this is positive and when this is negative, okay? So case 1. When it's positive, x has to be secant theta. If I draw this triangle, I'm going to draw it right here. Right, this is theta. And what we have is secant theta is x minus 1. And I told you not to put the variable up here, right? Because that goes into the quadrant and nothing exists in third, no inverse trig function exists in third quadrant. So this is 1 over x minus 1, isn't it? Say yes. That way, if it's negative, we can swing over to this side. You know what I'm saying? Which I'm going to draw later. Well then, x has to be more than 2. You know what I'm saying? Because this fraction, this is 1, and this cannot be greater than 1. So x has to be more than 2 in order to make sense. Good? Andrew, do you have a question?
Yeah, okay, so here we're not supposed to put the x on the hypotenuse, right? But like for number 5 on the Dropbox, you put the x on the hypotenuse. Like, when do we know when we can put the x on the hypotenuse?
See, number 5, it says x is greater than 2, which means x cannot be negative, so we are safe.
Okay, thank you.
Right? See, this putting it in hypotenuse business is dangerous because if I put the variable x minus 1 here, and in this case, x could be negative, then it swings over here. You know what I'm saying? We don't want that. But if we know this x is positive, and then there's only first quadrant, then we can actually put x here, and that makes our algebra a lot easier. Good? That clarifies everything? Okay. So, case 1, x has to be more than 2. Good? Okay, now, well, if that's the case, then this integral now becomes, they cancel, so it just becomes secant theta d theta, right? You want me to show you how to do that, multiply by secant theta plus tangent theta and do a u sub one more time, or are we good with this?
Wait, do we have to do that every time we get
No,
data?
you can just write this down. You can just do this. Because not that we are memorizing, but we can actually imagine this process, right? You don't have to show it to me. But in case you're wondering where that thing comes from, I can show it to you now. So does anybody want it?
Sure.
Was that yes?
Yes, I want to see.
Okay,
Again.
yeah, let's try that. So what we do here is this. Okay, I'm gonna do that with this. We are multiplying this thingy. In here, okay? What are we doing? We are just basically multiplying by 1. And 1 is the only number you can multiply and still claim it's the same thing. Then the numerator becomes this. And the denominator becomes this. Good. Then, now watch. If I let u to be secant theta plus tangent theta, and then du happens to be derivative of this, which is secant theta tangent theta, plus derivative of tangent, which is secant squared theta, whole thing times the theta. So this is du over u now, isn't it? And then we can kind of skip this step. I mean, the u sub is easy enough so that we can just write this down and not really make a substitution because it's ln u, and ln u is this. How about that? You get it? Okay, well then. Now, when you thought, okay, sure, we're done, right? No, we are not done. Why are we not done? We are not done because we have to bring x back, right? U, okay, so ln, what is secant theta? Secant theta up there was x minus 1, wasn't it? Okay, so we have ln and then x minus 1. I don't like that. And then plus tangent theta. God, we have to do this triangle thingy, right? But then, isn't this tangent theta right there? You know what I'm saying? Oh yeah, that's tangent theta. So this work has been done for us, right? I mean, we can still calculate it here if you want to. Do you want to see that as well? Or do you want to just take this? Tangent theta is this, which was really this thingy. You get it? So we can say tangent theta is square root of x squared minus 2x. How about that? So far with me? So far with me? And that's just case 1. Case 2. This thing is negative. If this is negative, then x has to be, is it less than 0, right? Yeah, x has to be, oh, on the Dropbox note I put less than 2. Less than 2? That makes no sense, right? And less than 0. I guess I'll replace that one with this thingy. Good. Okay, now, then what we have is, we can almost recycle our work now. So what that looks like is this triangular swing over to this side. And then this is 1 over. This side is 1 over x minus 1. So if x is less than 2, I mean less than 0, then this thingy becomes negative. You know what I'm saying? And then this side is still magnitude-wise, the length-wise less than 1, which is hypotenuse. How about that? Good. So if this is the case, then my integral becomes, this is my integral. It just becomes the opposite, right? Tangent still cancels, but this whole thing gives you -1, eh? So I have negative secant theta d theta. And lo and behold, this is exactly same as this thingy with a minus sign, so we can recycle our work and say negative ln x minus 1 plus square root of x squared minus 2x plus c. How about that? You get it? Are we good? Okay, that's number 15. Then number 22. Let's see, number 22 looks really ugly now, doesn't it? Okay, but I'm gonna let x to be tangent theta, eh? Okay, so let's do that. So if I let x to be tangent theta, and then dx is secant squared theta d theta, and that one was easy. How? Now this thing is not too bad. X squared plus 1, that becomes also secant theta, right? Good. Tangent squared plus 1 square root secant theta. Now, do we need absolute value here? Tangent, inverse tangent exists in quadrant 1 or quadrant 4, and secant is positive in both of those quadrants, right? So when you let x equal to some kind of secant theta is the only time we have to worry about that absolute value. You get it? Okay, but what we get out of this is quite ugly. Okay, let's look at it. Now, this is tangent cubed, right? Over, and then secant square over secant. So do you see that we have tangent cubed theta times secant theta? I'm going to move these guys over a little bit to make room. Do you agree with this simplification? Anybody lost? Okay, now we have to change this limits of integration whenever you change the variable. Otherwise, you have to write down x is equal to 0, x is equal to 1. So let's change it now. So substitute 0 here. This is the relationship between x and theta. So 0, so theta must be 0. And substitute 1 here, right? Tangent theta is equal to 1. So that tells you theta is equal to pi over 4. You with me? Okay, now this is an ugly integral, isn't it? So I'm gonna evaluate this separately on a side. Okay, because at the moment we have no idea, right? Yeah. Do I wanna change? Actually, maybe we can. I'll let you choose. Do you want me to just go on and change? This becomes a U substitution. So you want me to just change this limits of integration again, or do it on the side and plug it in? Who's the owner of this question? 22.
Do it on the side and plug in.
Side and plug it in. So let's do it on the side. Whenever you encounter something ugly, this is generally a good tactic. So let's integrate this thingy. Tangent cube theta, secant theta d theta. Okay. Now the tactic here is, of course, whenever you see this odd number, then you change square term, right? And then there's one tangent theta, and then there's a secant theta. So far so good? Now let's just think. Before you say, oh, and that do we distribute? No, let's just think. This secant tangent, that looks like derivative of this already now, doesn't it? So what we can do is u is equal to secant theta, then du is equal to secant tangent. And then what we have here is u squared minus 1 du. Ain't that nice? You get it? So what we're gonna have is now u cubed 1/3 minus u plus c. Now plug secant back in, so this is 1/3 secant cubed theta minus secant theta plus c. Say yes. Now we take that and shove it back in. Okay, so we come back here. That thingy is antiderivative of this thingy now. So we have 1/3 of secant cube theta minus secant theta, like that, and we drop c, and then pi over 4. You get it? Okay, and that looks like I stopped right there in the Dropbox note, but I just finished this off. So secant of 1/4, is that square root 2? Cube. So we have 2 root 2. So we have 2/3 root 2. With me? And then pi over 4 secant, so that's minus root 2. And 0 minus secant 0 is 1. So we have 1/3 minus, and this is 1, eh? Say yes. So looks like we have negative root 2. Why did I say 2 and root 3? Root 2 over 3 between the first two, and then plus 2/3, eh? How about that? Very good. Okay, so that's number 22. Do we have any more? Nope, that's it. Any questions before I start the recording? Lima.
Sorry, but is it okay if you try doing it the other way, that you like plug in for you?
Oh, you want me to do that as well?
If that's okay.
Oh yeah, of course it's okay. We'll do that. Edward, do you have a quick question before I try the alternative?
Yeah. So when we set like x equal to secant and then we get like tangent, for 19, how come tangent is an absolute value?
Okay, let me look at what 19 says. 19. Oh, because of I'm going to display 19 quickly so that everybody can look at what he's talking about. If we know that z is positive only, then we don't need an absolute value. So do we have any way of knowing that's the case? And sure, z varies from 1/√3 to 1, so they are positive. You see, this thing tells you, tricky, right?
Yeah, thank you.
No. And those are like pretty easy thing to overlook, but it is what it is. Anybody else with a question before I do the alternative way? Let's try the alternative way, okay? So number 22, alternative is, I'm gonna copy and paste. Let's copy this thingy and paste it here. And change the color. Let's do this in black. Change the color. I guess it's not gonna let me change the color, huh? Oh, it worked. So let's see the alternative way of evaluating this, okay? Okay, now we just make a u substitution here. Oh well, we still have to do this part. 0 to pi over 4, and this is secant squared theta minus 1, and then we have one of the tangent theta, and then secant theta, d theta, right? This much is the same, which is basically I'm doing this thingy over, but I'm carrying this limits of integration. You get it? So now I say u, so this is trig sub, now u sub, so it's the combination of the two. And then u is secant theta now. Good. And then u is secant tangent d theta. That's ugly. Why am I so anal? Don't answer that. Okay. Now, then we make a substitution here. So what happens is this is a u squared minus 1, and this whole thing is du now, isn't it? Now we have to change this limits of integration yet again. Okay, so it's like change a variable twice. So 0 here, if you plug in 0 here, secant theta is equal to 0, right? When is that the case? Oh, no. What am I doing? We have to put 0 here, right? So secant 0 is 1. So u will start from 1. Very good? That's ugly. Hold on. And then when we plug in pi over 4, secant theta is square root 2. Very good? And then if you lo and behold, see, square root 2 and 1. So it's the same thing. Actually, I prefer this way. You see how change a variable is nice? And then we evaluate, so this is u cubed, therefore 1/3, minus u from 1 to square root 2. You get it? So if we plug in square root 2, we get cube, so 2 root 2. 2 root 2 over 3 minus 1 and minus root 2, and then minus, if you plug in 1, you have 1/3, and then minus 1. And this is exactly the same thing as we had up here, isn't it? Do you see that? So we'll say, oh, this time I'm going to write 2/3 first, minus, what is this, root 2. over 3. You get it? Which is exactly the same answer. Wow. Okay, how do you like it? I like this way a lot. Okay, any other questions before I stop this recording?
Mr. Kim,
Yeah.
for number 15, why can it be x is greater than 1 and smaller than 1?
Let's look at it. You can actually write it like that, and I don't mind. But let's just think about it. Greater than 1. So here, if I put 1.1, right? I'm going to write it in here. So x is 1.1 is greater than 1, right? And this is 10. Can this side be 10 when this hypotenuse is 1? You know what I'm saying? It's kind of like mathematicians nitpicking, you have to be correct at all times thing. But if you're just talking about positive, negative, if you just put it, it's okay. I can't do it. You know what I'm saying? See, this side, the magnitude length of this needs to be less than 1, which is hypotenuse. So that's why I picked 2. But you can put 1 and it's fine. I don't care. I'll give you full credit. I'm just glad that you can distinguish positive, negative, and make 2 different cases.